Welcome in everyone. How's it going? Good evening, good evening. Hey Stephen. Nice to see you in here. How you doing? Welcome in everyone. Thanks for joining. We'll get started in a few. Let me know if you can hear me all right. Is the mic working? Pretty good. Enjoying my break. Yeah, I'm mostly writing right now, finishing up an analysis, trying to get published soon. So it's going pretty well. Matlick Chromodynamics, how's it going? I like the name. Got some QCD. Welcome in everyone. Thanks for the follow, appreciate it. By the way, tap that screen, make sure you're smashing that screen. Make sure you're always tapping, make sure your fingers are always like this. And some more people in here. There we go. That's what I'm talking about. Higgs boson. Yeah, we create it in these kinds of collisions actually, and it quickly decays. Were you that physicist I saw yesterday who was giving an inaccurate definition of singularity? I don't think I talked about singularities yesterday. I don't think I got questions about black holes yesterday. Maybe you're thinking of someone else. Can a photon particle be in two places at once? No, not really, but we can describe perhaps a probability of it being in one place rather than another. What's your favorite color? Blue? Question, is it possible to harvest energy from the Big Bang? So the energy coming from the Big Bang can often be thought of as maybe the photons that are coming from there, which we call the cosmic microwave background radiation. And unfortunately, it's very cold. You won't be able to use it to run anything. It's just really cold. So the answer is probably no. But in some sense, all the energy that we have in, for example, stars and stuff like that, ultimately that goes back to the Big Bang. So in some sense, when you use the power of the sun, which is a star, then you can trace that back all the way to the Big Bang. So in some sense, yes. What was happening before the Big Bang? We're not really sure. It's really hard to make measurements that go that far. Do you believe in cosmic dust? Yeah, there's dust everywhere actually, and it really makes observations difficult. Astronomers hate dust, cosmologists hate dust because it's everywhere. How difficult was your freshman year as a physics undergrad? So I took high school physics in Lebanon, which usually is kind of like maybe, I don't know, AP physics, I guess. And so when I came to the US, they wouldn't transfer my physics. So I had to redo, I guess, freshman physics. And I thought it was pretty easy just because I've taken it before. So in that sense, yeah, it was pretty chill. Sean Carroll spoke of the normal fields, but then said there was a universal field. Never heard of it. I'm not sure what the context of this is. I've never heard of normal field. Maybe I need some context for that. Can you get into particle physics with a nuclear engineering degree? Potentially, depends on how much math background you have and how much quantum mechanics you know. So there's a good chance that you might be able to transition some of that knowledge into particle physics. Do you have a community Discord? No, I don't. I don't like to keep track of stuff like that. I'd probably be terrible at running it. How does space expand and what does it expand into? That's a great question. So the space right now is expanding mostly because of two things. Number one, space usually expands because it started off in a state which was causing it to expand. And what we found recently is that it's actually expanding faster and faster. So if it's expanding faster and faster, there has to be something driving that expansion. That thing is what we call dark energy. Dark energy is the thing that we called that would drive the expansion faster and faster. Now the other part of the question was, what is the universe expanding into? So typically our minds are used to imagining maybe a ball in 3 dimensions, and that ball expands into a room. So there's always sort of a surrounding room, and maybe there's an object. And we like to imagine that this object expands in the room. When you talk about the universe is all there is, like this is what we are, right? So if the universe expands, what you have to imagine, maybe this would be a good analogy, is that take a number line. If you've taken math and you've drawn a number line before, and just imagine this number line goes infinitely to the left, infinitely to the right. What happens if I take all of the numbers on the number line and I double their values? Well, you still get a number line. You still get the same number line, except now all the numbers have changed locations. So in that sense, you can imagine a number line expanding without having to expand into something else. So hopefully that helps you think about the expansion of the universe. Let me multi-guess, please. Sorry, not doing multi-guess today. Sorry about that. I'm starting my final year of undergrad astrophysics this September. Any advice? Good luck. Try to think about where you want to be after you graduate. If you want to go to grad school, have you applied? Are you thinking of doing research? If you want to go into industry, how well is your coding? Do you have internships? Think about what you want to do after. That's always, going to be waiting for you when you get that diploma, right? And have fun. Like you're almost done. Good job, good luck, and be proud of what you accomplished. A number line is infinite. Is it the same for the universe? Potentially. We don't know if the universe is infinite or finite. I just gave the idea of the number line so you can imagine that you can expand without expanding into something else. Now it actually works even if the universe is finite in size. You would just describe the universe as a larger universe, but without having to describe something that's bigger than the universe. So it's completely mathematically legit to do that. Do tachyons really exist? No, we don't think they do. They're sort of mathematical artifacts. What is the shape of the universe? So shape typically refers to a square, a triangle, a circle, stuff like that. When we talk about the universe as a whole, then there's 2 ways to answer that. One is, what is the geometry of the universe? So that is asking questions like, is it curved or is it flat? And as far as we can tell, the universe is flat. Now the other question is not about the geometry, but it's more about the topology. So there's 2 things here: geometry, topology. When it comes to the topology, then the universe could be something like a 4-dimensional cube, if you want to include time, or just a 3-dimensional cube, if you want to include just space. But also it could be a torus. It could be a 3 torus. In which case it would still be flat, but now the topology is different in the sense that the universe has a hole in it. And you can Google what a torus is. Basically, it's a donut, and the universe could be a donut. Like, that's possible. I'm taking topology next semester, actually. Yeah, topology is one of those things that once you take it, you really expand your mind into thinking in such abstract ways that are very interesting. By the way, make sure you're tapping that screen, and if you're interested in these kinds of lives, hit that follow button right here. Appreciate you all and your questions. What about a Mobius band? Yeah, so a Mobius band is basically like a torus. It's kind of very similar to a torus. What particle is best tasting? I like to think that charm quarks are very flavorful. I guess neutrinos are also flavorful. There's a lot of flavor in the standard model. Say no to non-Euclidean shapes. We got some anti-Euclidean. Did the universe have a beginning? I would give it a 90% chance that the universe had a beginning. What are you doing at CERN? So I analyze data of collisions like this. So what we do is we smash protons together at really high energies, and you can see you produce like 500 different particles that go out, and you measure them, you measure all these particles, and you try to work backwards to reconstruct what actually happened right here in this collision. So that's what I study. I study these products out here and try to go back and understand what happened over here. Do you believe in Neil deGrasse Tyson? I think he's a very good science communicator. Do you believe in God? Yes, I do. Can you explain the atom bomb? Sure. So the basic idea is that there's a lot of energy that is stored in nuclei. So if you take uranium, for example, uranium has a lot of energy stored in the masses of nuclei. So what could happen is that if I can convert the mass of these neutrons or alpha particles or whatever, if I can take that mass and convert it into energy, then I can actually get quite a bit of energy from one single uranium atom. Well, what if I have trillions of uranium atoms? What if I cause a chain reaction to happen between many, many uranium atoms? So then each uranium atom can contribute some amount of energy, but if I concentrate all of that uranium next to each other, then I can get huge amounts of energy because of E is equal to mc squared. I can have some mass that gets converted into energy, and before you know it, you have a runaway reaction causing an explosion. How does proton therapy work? That's a great question. It's been a while since I've done medical physics, but if I remember correctly, proton therapy probably you utilize the gamma rays that are produced from accelerating protons. Those gamma rays end up hitting, for example, a cancer cell, and gamma rays have really high energies, and that energy ends up killing some cancer cells. So I think that's how it works, but I should probably look it up because it's been a while since I've looked at medical physics. Are you Muslim? Yes, I am. Why is the Hadron Collider so important? I mean, it's important for us scientists because we want to know what the universe is like. We want to understand the fundamental nature of reality. For the ordinary citizen, for the ordinary person who's not interested in science or the universe, the Hadron Collider doesn't really add much to their life. I'm just being honest. How can the universe expand and accelerate without needing more and more matter or energy? Yeah, so that's a great question. If you expand, then two things happen. The energy density of objects like radiation and matter, that goes down. But because dark energy is being, in some sense, created every time the universe is expanding, then there's new energy coming in from dark energy. So once you start thinking about the universe as a whole, the law of conservation of energy becomes kind of sketch. It's not really a law anymore. It's very weird if it actually applies or not. So cosmologists have some debate between them as to whether the conservation of energy really applies for the universe as a whole. You lost all credibility when you skipped my question. Okay, I don't know what you asked. There's a million questions that come by. Because you believe in God, why is that a problem? All right, I don't know. Someone's angry at me. How can there be nothing, no raw materials in all of space, and then all of a sudden a Big Bang? Yeah, so there's two things going on here. One is, what do we mean by the Big Bang? If you ask a scientist, a cosmologist, what is the Big Bang? They will never tell you that there was nothing and then something. Okay, if anyone ever tells you that the Big Bang is about nothing becoming something, they're lying to you. What the Big Bang is just simply describing the state of the universe 13.8 billion years ago. The state of the universe was really hot, was really dense, and was really compact. So when I say the Big Bang, I'm describing that state of the universe back in the day. Now, at that point, scientists split. Some scientists say the universe started at the Big Bang. That was like T is equal to 0. And then other scientists would say, no, that was just a transition period. The universe actually is infinitely old. That was just a transition period. Maybe before that universe was actually larger and it was contracting. Okay, that's where scientists split. But no one ever says that nothing created something. Okay, that's just nonsense. Are there wave physicists? There's no physicists that like study just waves, because waves, I mean, they appear everywhere. There's not like a study of just waves. So no. What is the first element of the universe? Hydrogen. Any new updates on WIMPs? As far as I know, we just keep excluding the parameter range, and we haven't found them yet, and it's not looking good for them. What did you do your bachelor's and master's in? I did my bachelor's in physics and math, and my master's, I kind of picked it up. It was on physics. Guys, make sure you're tapping that screen. I appreciate all your questions and the curiosity. And make sure to follow if you're curious and interested. How do you think the universe started or was created? So here I have to put sort of two caps on. My scientist cap is always, I have to ask naturally, how did the universe evolve from that state? So I am, full on the science all the way back. If it turns out the universe had a beginning, then at that t is equal to 0, I would say that God created the universe at that moment. If the universe is infinitely old, that would be a different story. Then you'd have to explain how the universe is infinitely old. But I will follow the science all the way. Like, if you're religious and you're listening, one thing that you should never do is stop an explanation too soon, right? You should always go with natural explanations. Always follow the law. Always follow natural law until you hit the final theory. Wimps versus machos. I lean wimps. What's the craziest thing that you've seen at CERN? I don't know. We discovered the Higgs. That was like superb. That was awesome. Stance on string theory. I think it's a very beautiful theory. I think we need it to make some testable predictions that we can somewhat verify currently. Otherwise, it's just going to stay in this limbo state of we don't know if it's true or not. But it's a very, very possible theory that could be a theory of everything. It's a good candidate. Any possible way that antimatter turned into dark matter? Not really, no, because we understand how antimatter works. So, if antimatter was dark matter, we would have explained it a long time ago, but it just didn't happen. Do you have any subatomic theories of your own? So I'm an experimentalist. I don't really theorize much about particle physics, but I go out and measure things, right? I work for CERN and we measure things and I collect data and I make the plots. So my job is to take someone's theory and try to say, it works or it doesn't work. That's my job. Do you think we ever exist again after death? Yeah, I think so. Let's talk about virtual particles and the use of the Casimir effect. Yeah, there's a lot of, I don't know what to call it, but there's a lot of talk about whether the Casimir effect is actually a thing or not. As far as I know from Wikipedia, there's been some debate about whether the Casimir effect was actually shown to be a force of virtual particles or whether it was some residual attraction between the materials or something like that. So it's not clear at all that the Casimir effect is real. Virtual particles, to me, they're just a mathematical trick that I use when I calculate Feynman diagrams. I don't think they're actually real. What other fields are there other than the Higgs boson? So we have basically 6 kinds of quarks. So up, down, charm, strange, top and bottom. So all of these come with their own fields. And then you have the electron, the muon, and the tau, in addition to the electron neutrino, the muon neutrino, and the tau neutrino. And all of those have their own fields. And then you have the photon, the gluon. They have their own fields. And you have the Z boson and the W boson. They have their own fields. So if you take all the standard model, all of them are described by fields. So it's not just the Higgs boson. It's basically every particle in the standard model has a field. All right. Any thoughts on time crystals and Penrose's, what is this? OR theory and Hamelrock's consciousness theory. Oh, I see. So Penrose has this idea that consciousness comes from microtubules in the brain. And in some weird way that I've never understood, the microtubules happen to be in a quantum superposition, and that ultimately leads to conscious awareness. Now, here's my problem. How do you go from microtubules plus quantum mechanics to consciousness? I never understood that gap. To me, consciousness is a mystery. I will never claim to explain what consciousness is. I don't think physics can explain it. Definitely not at the moment. Maybe in 1,000 years they would be, but like right now we have zero idea what consciousness is. It's just a mystery. How do non-perturbative effects influence the confinement of quarks within hadrons? So non-perturbative effects appear all the time in confinement because you're basically at the scale where perturbation theory doesn't apply. So the strength of the coupling has grown to the level where you can no longer write down a series expansion. How does it affect confinement? I mean, it's basically kind of when confinement happens, right? Like confinement is the idea that quarks and gluons are stuck, are bound with each other. And typically that happens at the lower energies, which is when you hit that non-perturbative regime. And there's a ton of work that is being done theoretically on calculating all sorts of non-perturbative effects having to do with the formation of pions and mesons, their fragmentation. So it's a very vibrant field. I personally know a few theorists that are doing calculations. I'm not a theorist myself, so I can't go into many details. Do you see the golden ratio appear much? Not really. In physics, we don't, find the golden ratio in our equations. But it does appear typically in nature whenever you talk about biological systems. Then you can expect the golden ratio to come up in certain biological systems. Is there a unified field theory yet? We have ideas. We have ideas like SU5, grand unified theory, SO10, grand unified theory, E8 by E8. There's a lot of ideas, but none have been shown. Microtubules produce the golden ratio? I've never heard of that. Physics 241 GSI, let's go. Nice to see you in here, Manav. How close to unified theory are we? Like I said, we have ideas, but we've never seen those ideas come to fruition. They're just theories. They're just people came up with things. We thought that they might be unified field theories. We haven't been shown to be true. What are virtual particles? So virtual particles are mathematical devices that we use in quantum field theory in order to calculate the probability of, for example, two electrons scattering. So what you can imagine is that these two electrons might emit a photon between them, so they interact via this virtual photon. And by putting in this virtual photon, you can make the calculation easier. And that's what we do in quantum field theory. So they're mostly a calculation trick. Why do we think photons are the force carriers for the E and M force? Magnetic fields don't give off light. It's because when you write down the electric field equations, so Maxwell's equations for electric fields, Maxwell's equations for magnetic fields, and you put them together in such a way to produce the wave equation, you can get light for free. So I know that I can put together electric and magnetic fields to obtain light. So if I just quantize my theory, I make it quantum mechanical, I get the photon. So I know immediately that the force carrier for electromagnetism is this wave that comes out of the electric and magnetic fields, which is the photon. How do you feel about the new research focusing on the neutron? It depends on what kind of new research on the neutron. You'd have to give me a bit more details. Can you talk about 1 over 137? So that number describes the strength of interactions between electrons, for example. It's called the fine structure constant, and it describes how strong electromagnetism is. So just as a way to understand the strength of a force, right now the entire Earth is tugging on my earphones, and yet here I am, a feeble human being. I can raise my earphones higher up. So the whole Earth is tugging on this, and yet I can lift it. So how is that possible? It's because I'm using forces of electromagnetism, whereas the Earth is using forces of gravity. But electromagnetism is so much stronger than gravity. How do we know? How do we characterize the strength? We use that number called the fine structure constant, 1 over 137. And for gravity, it's like way, way lower. Where has Quanta been? He's been around. I've seen him here and there, but he hasn't been going live recently. He's probably busy in the lab. But if he's in here, then he's welcome to join. Do you use group theory? Yeah, actually, I use group theory all the time because the standard model of particle physics has a language to it. That language is group theory. So just as an example, the standard model of particle physics is written as a direct product of three groups. Those groups are Lie groups, and they're called SU3, so special unitary groups of 3 by 3 matrices. That describes the strong nuclear force. SU2 cross U1, that describes the electroweak force. So SU2 is the special unitary group of 2 by 2 matrices. And actually it's called SU2 left because the weak force only interacts with left-handed particles. That's, a whole thing on its own. And then U1 is called U1 hypercharge because in the electroweak theory you have something known as isospin and something known as hypercharge. And these two things in the electroweak force basically describe the electroweak force. So you have the strong nuclear force, SU3, and then you have the electroweak force, which is SU2 cross U1. It sounds hella made up. Yeah, I mean, you can Google SU3 times SU2 times U1, and you'll see a whole Wikipedia page just for it, the group theory behind it. By the way, make sure you tap in that screen if you're enjoying the live and hit that follow button if you're a curious person. Should I major in physics? Only if you truly, deeply love physics and you can't see yourself doing something else. What is the neutrino? And what is the anti-gravity particle? So a neutrino is a funny little particle. It only interacts with things via the weak nuclear force. So we know that there are 4 forces of nature: the strong nuclear force, gravity, electromagnetism, and the weak nuclear force. Neutrinos decided to be decided to be a pain in the butt. They only interact with matter through the weak nuclear force and gravity. But gravity is already really weak, so the weak nuclear force is all we got. That is to say that a neutrino is kind of like a ghost. It goes through things unimpeded for ages. And then at some point, after light years and light years of travel, it decides to interact with a particle. So they're really pesky tiny little particles that take ages to detect. So the way we find them is by taking gazillions of them and just hope that a few of them interact with our detectors so you can see a little bit come up. As for an anti-gravity particle, there's not really an anti-gravity particle. The best thing you can come close to is dark energy. Dark energy has an anti-gravity effect because it expands space outwards. Yeah, right now there's about 1 trillion neutrinos passing right through your body and you don't feel them. They're kind of invading your personal space, but what can you do? Are anti-neutrinos still a thing? Of course they are. Can we create antimatter? There's a lot of antimatter being created right here. So in proton-proton collisions, we create antimatter all the time. Is quantum computing going to be big? Personally, right now, I don't see it, but I hope to be proven wrong. What happens if 2 black holes collide? You'd get a lot of gravitational waves that come out, and I believe you get a larger black hole. Do you need real analysis, complex analysis for physics? You mostly need complex analysis. Real analysis is mostly just to, I guess, prime your brain into thinking mathematically, but I don't see it being used that often. Now, topology, on the other hand, probably comes up more, and group theory, abstract algebra, comes up all the time. How can I imagine that one turn for the fermion spin is 720 degrees? That's a great question. That's a great question. Hold that thought. Hold that thought. Here's a mug. Okay, it says, "You the best, engineer." Okay, it's my wife's mug. So how can I imagine fermions? Here's a mug. So watch what's gonna happen. I'm gonna hold the mug outward like this, and I want you to keep track of Yoda, okay? So I'm going to first rotate my hand 360 degrees. So now you can see Yoda is back to where he was. But notice my elbow is flipped. So 360-degree rotation gives me a flipped elbow. And then I rotate another 360 degrees. And now my hand is back to normal. You can see that Yoda is back to normal. So it took me actually 2 rotations to bring my arm back to where it was. So fermions, electrons, are like this. They need not 1 rotation. They actually need 2 rotations to come back to their spin state. So this is what we call a spin 1/2 particle. And this is often called Dirac's belt trick. You can look up YouTube videos about that as well. So that's one way to think about it. Is he getting a belt? Yeah, I was getting a mug, but you know, same thing. PV is equal to nRT. Let's go. I'm glad you like that explanation. Do you have a personal belief on what dark matter is? Example, right-handed neutrinos. I used to think it was WIMPs because I believed in the WIMP miracle, and then it didn't work out. So now I'm kind of like in the dark. I don't know. I have no idea what dark matter is. Explain Hawking radiation. Is it related to entropy? That's something that is truly beyond my pay grade because it requires quantum field theory applied to curved spacetimes. But I've never taken general relativity, so I don't know how to deal with curved spacetimes. So for me to try to explain Hawking radiation would be nonsense because I don't really know how that works. How does Compton scattering and pair production work? Sure, so Compton scattering is the idea that if I have an electron and I shine a photon on it, then I can get these two to interact. Why? Because the electron is charged, and charges interact with light, with photons. So if I have really high energy photons, I can smash them with electrons, and that photon's wavelength would change. So in a sense, the photon energy is going to change, its frequency will change. So that's called a scattering between a photon and an electron, and that's called Compton scattering. On the other hand, you can have pair production, which is if I take 2 gamma rays, then they can create an electron-positron pair. So an electron-positron pair is what we call a pair production, an electron and an anti-electron. So you can have photons that turn into electrons and positrons. Is that a free electron? Yeah, typically Compton scattering happens with free electrons. By the way, thank you for the follows. If you're enjoying this live, hit that follow button right here and make sure you tap that screen. I appreciate all the curiosity and all the questions. Can we rewatch these later? I don't record these. I think TikTok probably records them, you know, just by default. If you're interested, then I can upload these to my YouTube channel. Go to my page, click the link tree, and then go straight to my YouTube channel. You can subscribe there, and I'll probably upload this Q&A on YouTube. That way you can watch it later. But yeah, I don't usually like post clips or anything like this on TikTok. Did you manage to find Clauser's paper on Bell's inequality? I actually didn't look, so I'm sorry about that. I was busy with other things, but let me look right now and find it for you. Clauser, okay. Right, so here it is. It's called Proposed Experiment to Test Local Hidden Variable Theories. So this was, actually if you just go to Google Scholar and you type in John Clauser, then basically the first 3 papers, or the first 4 papers, are basically his work on hidden variable theories and Bell's inequalities. So just go to Google Scholar and type in John Clauser. What will happen if the strong nuclear is much stronger? Yeah, so that would be catastrophic, actually. There's a really good book by Luke Barnes, and where is it? Somewhere here. And Geraint Lewis that talk about the fine-tuning of the universe. So here's the book. It's called A Fortunate Universe. And you can start asking questions like, what happens if I mess around with the strength of the strong nuclear force, or electromagnetism, or the masses of particles, or the rate of expansion, and stuff like that. And you'll quickly find out that if you change things by a little bit, chaos ensues. Chaos or supersymmetry? I'm not sure how those are like two options out of something. Preferred quantum interpretation. I used to be a Copenhagen kind of person. These days I think it's kind of incoherent. So I lean towards GRW theories, which are also called spontaneous collapse. So for those who don't know, Copenhagen posits that every time you make a measurement, then the wave function collapses. Of course, what do you mean by measurement? I mean, no one was ever able to define what that is. On the other hand, spontaneous collapse theories say that the wave function collapses on its own. It's just a stochastic process. There's some probability that it just collapses. And that makes more sense than invoking some measurement. Which is more difficult, physics or math? I think math is more difficult. Let's make sure we're tapping that screen to get up to 10K right here. Make sure to hit that follow button if you're enjoying these Q&A. Is the Milky Way moving around the universe? So your question sort of implicitly has a center of the universe that the Milky Way would go around. But there is no center of the universe, so the Milky Way doesn't really go around something. What was your favorite physics class and why? It was the classes that we took together, Nick. So those were my favorite classes. Tell me about the particle accelerator. Sure, so this right here behind me is an example of a collision that happens in a particle accelerator. You can take something like a proton and you can accelerate it using an electric field to make it go at 99.9999999% the speed of light. And then you can collide two of them together. So there's a lot of energy packed into a small space. And because you dumped in a lot of energy, then you can actually start creating new particles, all this stuff that comes out. And we basically measure things out here in the detector, and we try to work backwards to see what happened in the collision point. So we try to create new particles, we try to create the conditions that were at the Big Bang, just to study science in the universe more closely. Is there a facility for rare isotopes and collisions? Yeah, it's called the FRIB. It's at Michigan State University. It's pretty cool. Check it out. Do you recommend books for quantum particle that is easy to understand? I don't know about easy to understand, but there's a lot of science popularizers that have written books about quantum mechanics. So I know Sean Carroll has some books. I know Brian Greene has some books. Who else? Quantum mechanics. Probably Neil deGrasse Tyson has written something. But I don't know what's the best. So I'm sorry about that. Why can't we store dark matter? It's because we don't know how to interact with it. If we knew what it is and how to like interact with it, then maybe we could store it. But also you have to remember that dark matter probably doesn't interact much with things. So it will just go straight through, a detector unimpeded. So it's hard to contain. Do you think that physicists have to take too many math classes? I think they don't take enough math classes, to be honest. Do you believe in a simulation? No, I don't. How does the multiverse theory work in the Big Bang? Those two are kind of not really related unless you invoke inflation. So they're not really related. How accurate is the Big Bang theory? Very accurate, actually. By the way, he means the show, or she means the show. And they actually get the science pretty dead on. All right, so I'm getting kind of tired. It's getting late. I appreciate all your questions. If I didn't get to your question, I'm sorry, but there's just a whole lot of them that keep on coming. Make sure you hit that follow button so you don't miss the next live. And make sure to check the link tree in my profile so you can go to my YouTube if you want to see this uploaded to YouTube. So I appreciate all your questions. I appreciate the curiosity, all the follows, all the likes. You guys are awesome. Make sure to send me your questions as DMs if I didn't get to them. So with that, have a wonderful rest of your evening or a good day if it's day. I'll see you next time. So have a good one.